This video is going to cover the tutorial solutions for topic 11 on how does a nuclear power plant work. Problem 1. We're told that the nucleus in a typical atom has a radius of 10 femtometers. So we know that the nuclear radius is about 10 times 10 to the minus 15 meters. And an atom has a radius of 1 angstrom. So R for the atom is approximately 1 times 10 to the minus 10 meters. Now, part A asks us to calculate the volume of the nucleus. So the volume is equal to 4/3 pi the nuclear radius cubed. This is just the volume for a sphere, so we're just going to substitute into this equation. So this is 4/3 times pi times 10 to the minus 15, all cubed. And so solving this one on the calculator, we end up with 4 times 10 to the minus 42 meters cubed. So this is just to one significant figure because these values are only given to one significant figure. Now part B says calculate the volume of an atom. So we use the same equation now. We've got 4/3 pi, but now instead of the radius of the nucleus, we use the radius of the atom cubed. So this is 4/3 pi times 1 times 10 to the minus 10 all cubed. And solving that on the calculator, we get 4 times 10 to the minus 30 meters cubed. And so part C then asks what fraction of the atomic volume is filled by the nucleus. So this is the volume of the nucleus, this is the volume of the atom. So what we will have is the volume of the nucleus over the volume of the atom, which is equal to 4 times 10 to the minus 42 over 4 times 10 to the minus 30. These 4's will cancel out and we'll end up with 10 to the minus 12 is the fraction of the atom which is filled by the nucleus. So a tiny part. So we can either leave our answer as 10 to the minus 12, or if you want to give it as a percentage, then you divide it by 100. So it would be 10 to the minus 14%. Part D then asks us, is it true that the atom is mainly empty space? Well, yes, because electrons don't take up any space, and you can see that this nucleus hardly takes up any space, so almost all of the atom is actually empty space. Problem 2. In this problem we have a graph showing the binding energy per nucleon. So this is the amount of energy which is released when these nucleons are put together. So in part A, we're asked how much energy is released when we form a 4 helium nucleus. And this comes from 2 protons plus 2 neutrons. Now, protons and neutrons don't have any binding energy to start with because they're just individual particles. So what we need to do is look for helium-4 on this graph, which is here, and this tells us that helium-4 has a binding energy of 7 mega electron volts per nucleon. Now in helium-4 there's 4 nucleons, the 2 protons and the 2 neutrons. So this tells us that the binding energy is just equal to the 4 times the 7 mega electron volts, so that's 28 mega electron volts. Now in part B of the question, we're asked how much energy would be released if we assemble iron 56. So we're going to end up with iron, which has 26 protons and 56 nucleons, and we're going to assemble this from 11 helium-4 nuclei and 4 hydrogen-3 nuclei. So there's 4 of these, and we can just check that the numbers add up. Let's check the atomic numbers. 2 times 11 is 22, plus 4 gives us the 26. For helium, we've got 4 times 11, which is 44, plus 4 times 3, which gives us the 56. And so to find the binding energy released, what we have to do, this is equal to the binding energy of 5626 iron minus the binding energy of the 1142 helium plus the 431 hydrogen. And so this is equal to, now for iron 56, we can read it off here. If we bring a straight line around along there, that is around about 8.75. And we have 56 of those nucleons. And then we have to subtract off these. So with this, this is the helium here. So the helium had 7. And there are 4 times 11 of those nucleons. And now the hydrogen 3, when we read that off the graph, here's the hydrogen 3. So that's around about 2.75 mega electron volts. So that's plus the 2.75. And then there are 3 nucleons in each of those hydrogen atoms. And there are 4 of those hydrogen nucleuses in total. So now we've got just an equation to solve on the calculator. When we type this in, we get 149 mega electron volts. So this is the amount of energy that is released when we form this iron 56 nucleus. So part C says explain why isotopes with A less than 56, so that's down here, tend to undergo fusion, while isotopes up here tend to undergo fission. Well, fusion is when they come together. So these ones which are lighter than iron, if they fuse together, they will enter a lower energy state, they'll release more binding energy, and everything in nature wants to try and get to the lowest energy state it can. So atoms, let's not call them atoms, let's call them nuclei. Nuclei with A less than 56 can release energy by undergoing fusion, which is sticking together. And then these ones up here release energy by becoming smaller, so by fissioning or breaking apart. Nuclei and systems tend to the lowest energy state. So that is why it occurs. Problem 3. In this problem, we're told that a common nuclear decay in nuclear power plants is 10N plus 23592 uranium going to, well, this forms 23692 uranium, which is unstable, and then can decay into 14356 barium and 9136 krypton plus 2 neutrons. And we're told that the mass of uranium-235 is 235.0439 atomic mass units. The mass of barium is equal to 142.9206 atomic mass units, and the mass of krypton is equal to 90.9234 atomic mass units. And in part A, we're asked how much mass is lost during this decay. So the mass loss is equal to the mass that we start with, so the mass of, let's call them the reactants, minus the mass that we end up with, so the mass of the products. So this is equal to the mass of 10 nitrogen plus 235.92 uranium minus the mass of 143.56 barium plus 9136 krypton plus 210 neutrons. Now this neutron will cancel out one of these neutrons here. So now we can just substitute everything in. We've got 235.0439 atomic mass units minus 142.9206 atomic mass units minus the krypton, which is 90.9234 atomic mass units. Now we have to subtract off the mass of the neutron. We're given that at the front of the tutorial problems as 1.675 times 10 to the minus 27 kilograms. To get that into atomic mass units, we need to divide it by one atomic mass unit, which is 1.661 times 10 to the minus 27 kilograms. So the 10 to the minus 27 will cancel each other out. And then solving this thing on the calculator, we end up with 0.01915 atomic mass units. We can also present it in kilograms. If we times it by 1.661 times 10 to the minus 27 kilograms, we will convert that into kilograms. So we could also give it as 3.180 times 10 to the minus 28 kilograms. And now in part B, we're asked to calculate the amount of energy released. So this is just going to be mc squared, where m is the mass lost, so that's this. 3.180 times 10 to the minus 28 times 3.00 times 10 to the 8 squared gives us an answer of 2.86 times 10 to the minus 11 joules. And we can convert this into electron volts if we want by dividing by 1.602 times 10 to the minus 19. So this is equal to 1.79 times 10 to the 8 electron volts, or 179 electron volts. Now part C of the question says that another possibility is that uranium-235 becomes barium-141 and krypton-92, and we need to write the equation for this. So we've got the same on the left-hand side, 10 nitrogen plus 235 92 uranium becomes the 236 92 uranium, and then this decays, but now we're getting 141 56 barium plus 92 36 krypton, and now we need to work out what happens to the neutrons. So on the left we can see that 92 plus 0 is remains at 92. 56 plus 36 is 92. So the atomic numbers are all balanced. We need to work out the mass number. On this side it's 236. On this side we've got 141 plus 92. That is equal to 233. So we need another 3 neutrons. So this is plus 310 neutrons. So this is a bit of a mess, but that's our equation there. All balanced now. So if we get these products, we end up with 3 neutrons. So then it asks us is which one's more likely to cause a chain reaction and why. Well, the answer is this one. So 141 Ba 92 plus 92 krypton is more likely to cause the chain reaction because it releases more neutrons, and the more neutrons that get released, the more reactions that this can start, because this can now start 3 reactions, whereas this one up here could only start 2 reactions. So this one is more likely to start a chain reaction. This is problem 4. In this problem, we're asked to write down the equation showing atomic number, mass number, and symbols to describe alpha decay. Well, first of all, alpha decay of 21184 polonium. Okay, so this is alpha decay, and so we are going to get an alpha particle, 4,2 helium, and then to balance the numbers, the atomic number down here must be 84 minus 2, which gives us 82, and the mass number will be 211 minus 4, which is 207. And now what we have to do is get a periodic table and look up what is element number 82, and we find that element number 82 is lead, Pb. So this is the alpha decay equation. Now that's one. Question 2, we now need to do the alpha decay of 24292 uranium. When we do that, we get an alpha particle released, and then our atomic number is going to be 92 minus 2, so that's 90. Our mass number will be 242 minus 4, so that gives us 238. And then we look up what element number 90 is, and element number 90 is thorium. So that's helium plus thorium. And now part B, we're asked to do the beta decay through the negative beta release, or the release of an electron, of first of all boron. So this is boron 14, and it's releasing a beta particle, which is E minus 1, 0. And so 5 plus 1 gives us the 6, and then 0, so the mass number remains the same. Element number 6 is carbon. So this side we've now got 5 down the bottom, which balances this 5 here. So this describes the beta decay of boron 14. And then we need to do the beta decay of osmium 191. And so once again we get a beta particle produced, and then we have 76 plus 1, which gives us 77, 191. When we look up what element 77 is, we find that it is iridium. And C, we now have the release of a positron. So the first one that decays through the positron decay is nitrogen 13. And so we're releasing a positron, which looks like this. And so we end up with an atomic number 1 less than 7, so that's 6. This is unchanged. 6 is carbon. So we've got this as our equation. And then next, we're asked for the positron emission from bismuth 207. So 207 bismuth, which has an atomic number of 83. We will release a positron, and so we'll end up with something with an atomic number 82, 207 is the mass number again, and element 82, as we've said, somewhere up here it is lead. So that's how we do question 4. Problem 5. So we're told that gold 198 has a half-life of 2.69 days. And it's used in cancer therapy, and we have an initial mass, so the initial amount present is 0.500 grams. Then in part A, we're asked how much remains after 4 half-lives. So the amount remaining is equal to the initial amount times a half to the power of the number of half-lives. As each half-life, half of it disappears. So we've got 0.500 grams times a half, and then it's 4 half-lives, so this half is to the power of 4. And so solving that one on the calculator, we end up with this is equal to 0.031 grams. Now, part B asks us, what is the decay constant lambda equal to for this reaction? Well, we know that the half-life is related to the decay constant through log 2 divided by the decay constant is equal to the half-life. So this, just rearranging this, tells us that the decay constant is equal to log 2 divided by the half-life. So if we want this in per day, then we've got log 2 over 2.69, and solving that on the calculator, we get 0.258 inverse day. The other option is we could get this into inverse seconds, so we do log 2 divided by this time in seconds, should be 2.69, that's the number of days, times 24, there's 24 hours in a day, times 60 times 60. So this converts it into hours, this one converts it into hours, this is into minutes, and this converts it into seconds. And so solving this one on the calculator, we end up with 2.98 times 10 to the minus 6 inverse seconds. Now part C asks us after what length of time will only 0.010 grams be remaining. Well, our equation to describe the amount remaining is the amount remaining is equal to the initial amount times e to the minus lambda t, which is what we use this decay constant for. So we want to have 0.010 grams, and we start with 0.500 grams, and this is e to the minus. Let's get our time in days to start with, so that's 0.258 t, and this time is in days, and so we divide this by this, and we end up with 0.020 is equal to e to minus 0.258 t, and now we're going to need to take the natural logarithm of both sides in order to get rid of this exponential. So doing that gives us log of 0.020 is equal to minus 0.258 t, and so t is equal to 15.2 days. Now if we wanted to do it in seconds, we would use this decay constant here instead. So this goes down here instead, and then our answer would be in seconds. If we do that, then we end up with the time in seconds being 1.31 times 10 to the 6 seconds. But this number, 15 days, is probably a lot easier to visualize. Problem 6. This problem says food irradiation is a process in which food is bombarded with nuclear radiation in order to kill off microorganisms. A. Refer to the properties of alpha, beta and gamma radiation to describe which would be the most appropriate for this process. Well, for this process we're going to want to use gamma radiation as it's got the most penetrating power. Alpha radiation probably wouldn't even get through the packaging, and beta radiation would be stopped within centimeters of entering, so there's no way that it would irradiate all the food. So let's write that down. Alpha radiation has very low penetrating power, and so would not pass through the packaging. Beta radiation would only penetrate the very top of the food. So gamma radiation is the most appropriate. Now part B says, would this make the food radioactive? Well, no, it would not, because gamma rays can't actually knock protons or neutrons out of the nucleus. And so as we can't change the nucleus, we can't make it become radioactive. So this is another reason for using gamma radiation. If you were using alpha radiation, if it could penetrate, then it can change the nucleus and it could make it radioactive. So no, gamma radiation can not knock protons and neutrons, so we should say all neutrons out of the nucleus. So it cannot cause food to become radioactive. And then part C says, could irradiating the food do anything other than kill off the bacteria? Well, yes it can, because gamma radiation, well yes it can. Gamma radiation can affect the electrons which are around the atoms. It can knock the electrons out because it does have a low ionizing power, and so this can affect the chemistry that is involved, and so it can change the molecules. So let's write that down. Yes, gamma radiation can ionize atoms and affect the chemistry. This is why it is only permitted for some food items in Australia. So Australia has fairly strict rules about the irradiation of food. Some countries allow it a lot more, but in Australia they want to hold off on allowing it until there's a lot of evidence that it is very safe. And it is possible that it may affect the chemistry. This is problem 7. In this problem we're given 5 loops, 1, 2, 3, 4, 5. And we're told that all are made from the same wire and that these first 4 are identical, and then this one has the same height but it's longer. And they're all moving at the same speed in these directions showing. There's a uniform magnetic field here but no magnetic field in region 2. And we're asked A, for any loop that has an induced current, indicate the direction of the current. Okay, so in order to get an induced current, we need to have an EMF, and the EMF is given by Faraday's law. It's equal to minus d phi b dt, which means we need a changing magnetic flux. And remember that the magnetic flux is equal to BA cos theta. And diagrammatically, it's just the number of magnetic field lines that are passing through the loop. So what we need to have is a changing number of field lines. So if we have a changing number of field lines passing through our loop, then we will have an induced EMF and we will have a current flowing. Okay, and from Lenz's law, this tells us that current will flow to oppose the change. Okay, so let's keep that in mind and consider each of these loops. Okay, so loop 1, the loop is moving to the right, and so as it moves there's less and less magnetic field lines going through it. Let's grab a different colour, because less and less of it is in this region, and it's only the bit in this region which contributes to this. So this one has decreasing phi b. Okay, so what's going to happen is it's going to have current flowing through it, and that current's going to flow to try and induce a magnetic field which is coming out of the page as well, so that it adds to this one here. So now that we've worked out in which direction the magnetic field is going to be induced, we can work out in which direction the current flows. The current is flowing around the loop in this direction. So we can just use the right hand screw rule to show that. If you align your thumb with the current flowing in this direction, then your fingers are pointing up out of the screen. So loop number 2 is now in region 1, and the magnetic field lines, the number of magnetic field lines in here are not changing. So B is constant inside loop 2, and so there's no current and no induced EMF. So no induced EMF. Okay, loop 3 here, we'll do this one in yellow. Now, as this one here moves up, we've still got the same number of magnetic field lines going through it, because half of it is in the magnetic field, half of it is not in the magnetic field. So the area inside that magnetic field is not changing, so no EMF and no current. Okay, loop 4. It's getting more and more magnetic field lines flowing through it, because more and more of its area is moving into this magnetic field. So this one here has an increasing 5B. So Lenz's law tells us that the current's going to flow to try and reduce that magnetic flux. So how's it going to do that? Well, if it creates magnetic field lines going into the page, then these will cancel these magnetic field lines coming out of the page. So in order to create magnetic field lines going into the page, the current is going to have to flow this way around the loop like that. Now with loop number 5, it's a bit longer than loop number 4, but it's traveling in the same direction. So again, it has an increasing magnetic flux. So again, we're going to get an induced magnetic field to try and cancel that out. And so we're going to have induced magnetic field lines going into the screen. And so the current is going to flow this way around our loop. So that's the answer to part A. Part B, rank the magnitude of the EMFs around the loop. Explain your reasoning. Okay, well, we've said that some of them have 0. 2 and 3 have 0. Okay, now to rank the EMFs around the loop, what's changing is the area of the loop within the magnetic field. So we're going to have that our induced EMF is equal to minus B times the change in the area dt, and these all have the same height, so the area is equal to the height, and then if we do this length as x, so we can refer to just x as the area inside the field, so we've got minus bh and then dx dt, but this is how fast the area within the field is changing, and that change is caused by this velocity here. So this is equal to minus bhv. And so from that logic, bhv is the same for 1, 4 and 5. For 2 and 3, we've said that there is no induced EMF because the B isn't actually changing. So this A is the area within the field, and that is not changing for 2 and 3. So we have that the EMF, let's call it V1, is the same as V4, is the same as V5, and all these EMFs are greater than V2 and V3, which are equal to 0. So part C, rank the magnitudes of the currents in the loop, explain your reasoning. Well, if there's no induced voltage, then the current's going to be 0. So we know that I2 is equal to I3 is equal to 0. And now loop 1 and loop 4 have the same length, and they have the same voltage, and so they're going to have the same current. Just because V equals IR, as they have the same length, they have the same resistance. Loop 5, on the other hand, is longer. We've got more wire, and if there's more wire, there's more resistance. So 5 has more resistance. So that tells us that same V gives the same voltage implies less current. So the current around 1 will be the same as the current around 4, as they've got the same resistance and same voltage. That'll be greater than the current around 5, which is greater than the current around 2 and 3, which is equal to 0. So question 8 says, why doesn't uranium-238 undergo spontaneous chain reactions in nature? And it tells us that this is a research question, so we'll need to do a little bit of research. So when you look up some information about your uranium-238, you'll see that U-238 is very stable. So by definition, things which are very stable are unlikely to decay. So that's part of the reason it doesn't undergo spontaneous chain reactions in nature. So evidence that it's very stable is that it has a half-life of 1.41 times 10 to the 17 seconds, or we can give this in years as 4.5 times 10 to the 9 years. So we can get uranium-238 to decay, but in order to do that, what we actually need to do is get it to collide with a slow-moving neutron, which will stick to it and make uranium-239. And this is not very common in nature. So in order to cause it to decay, it needs to have a neutron added to it. Slow moving neutrons are not especially common in nature. In power plants, obviously we're talking about nuclear power plants, this is achieved through a collision with a slow moving neutron. So neutrons are slowed through collisions with generally heavy water. You can do it with normal water as well, but heavy water works a little bit better. So it then becomes uranium-239, and this decays to fissionable plutonium. So let's show that series of things. So we've got the 238, 92 uranium mixes with a slow moving neutron which sticks to it, giving us 239, 92 uranium, which is then unstable. This undergoes beta decay, becoming, or anti-beta decay, 239, 93 neptunium with the release of an anti-beta particle, and this then decays into plutonium through another anti-beta decay, and this is fissionable, meaning that it'll break apart into two separate nuclei spontaneously. Problem 9. Now this problem is actually about an electric motor. So it tells us electric motors are found in many electrical appliances. They work like generators but in reverse. The alternating current flowing through the coil of wire causes the coil to experience a force. This force starts the coil turning, converting the supplied electrical energy into mechanical energy. In the diagram below, which is just here, the magnets have a magnetic strength of 1 Tesla. So let's draw in the magnetic field lines to start with. So the magnetic field lines go, So the magnetic field lines go out of the North Pole and into the South Pole like this. So we have magnetic field lines like this. Now, these two poles would be joined together in a horseshoe magnet, but that's not shown at the moment. We can't have just one North Pole by itself. And we're told to assume that the magnetic field strength in here is 1.2 Teslas and that there's 10 turns of wire. So here N is equal to 10. So in part A, we're asked to consider the left-hand side of the coil. So we're considering this bit along here. So the current is flowing up like this. So consider the left-hand side of the coil parallel to the pivot axis with a length of 10 centimeters. As a current of 2 amps flows through it, we're asked what force does it experience. So we're going to have to use our formula for the force on a current carrying wire in a magnetic field. So that will be F is equal to BIL sine theta that we learnt about in the last topic. But we have N turns of wire here, so N times that. And so substituting in, we've got 10 turns. The magnetic field strength is 1.2 Teslas. The current is 2 amps. The length of this side is 10 centimeters, so 0.10 meters. Sine theta, that is the angle between the magnetic field and the current. So you can see it's 90 degrees. So times sine 90, which is 1. So solving this on the calculator, or in your head if you want, this is equal to 2.4 newtons. Now, as it's a force, we need to give a direction as well. So you'll need to use your right hand, align your fingers with those magnetic field lines, and your thumb with the direction the current is flowing, and you can see that your palm is going into the screen or into the page. So that is the direction of the force. So into the screen page. Now, part B of the question asks, what is the force on the right-hand side at the same moment in time? So now on the right-hand side, we've got the current flowing down in this direction. And then once again, we'll have F is equal to NBIL sine theta. You can see all these terms are going to be identical to up here. The length's the same, the current's the same, the magnetic field's the same, and the number of turns is the same. The only difference is that if we use our right hand rule now, our palm is pointing up out of the screen. So it's going to have the same magnitude. So this will be 2.4 newtons, but in this case it will be up, out of the screen. Okay, so part C then says these forces produce a torque or a turning force. So torque can be calculated using the formula torque is equal to force times d sine theta, where F is the force, d is the distance from the pivot point or axis, and theta is the angle between the force and the distance from the pivot point. So the distance from the pivot point is taken as this direction, going from the pivot axis in this case to where the force is applied, which is along these wires here. So part C, what is the torque at this point in time? Well, what we're going to have to do is calculate the torque along each part of this coil here. So let's start with the torque along this left-hand side here. Let's call it torque left. Well, we've calculated the force up here, so it's 2.4. Now, d, that's the distance, and the distance of this side from the pivot axis is 5 centimeters, so times 0.05. Now, times sine theta, and theta is the angle between this d thing, which is in this direction, and the force, which was up, well, down into the screen, so that is 90 degrees. And so solving this, we end up with 0.12 Newton meters. And this, if we're looking at it from this end, so if we imagine looking at it from that direction, then this is going to try and get it to turn counterclockwise. When looking from here. And then the torque on the right hand side, the force is the same, the distance is the same, and once again this is d, and the force in this case is up out of the screen, so the angle between those two is 90 degrees. And now this one is also getting it to try and spin counterclockwise when looking from this direction. Okay, so we're going to have to add together all the torques around this loop. Now these two sides here don't experience any force as the magnetic field lines and the current are parallel, so no torque here as no force, and we need to have a force in order to have a torque. So we just need to add these two torques together. So the net torque is equal to 2TL plus tau R. Because they're going in the same direction, we add them together. So this one, when we evaluate that, that's 0.12. So we've got 0.12 plus 0.12, which is equal to 0.24 Newton meters, and it's going to try and get it to turn counterclockwise when we're looking from this direction. Okay, now part D. Will the size of the torque change with time If so, describe this change. Well, when we start off, when we're looking at it from this end, it looks something like this, and this is our D here. But after a little while, it has become like this. Now, this d sine theta part of it is actually this distance here, so d sine theta. So when it's turned in that direction, you can see this has d sine theta is equal to d. Here d sine theta is getting smaller, and here d sine theta is actually 0. The horizontal distance from this axis is 0. So the torque decreases as the coil becomes vertical. And so it's going to be, it's 0 when coil is vertical. So that's when we're looking from this end, and when the coil's aligned like that, then there is no torque. So E, what would be the effect of using an alternating current in a setup like this? Well, what we can do is, if we get the coil turning at the same frequency that the alternating current's changing, is that we can actually get it to go as a continuous motor. Because what happens is this torque decreases and decreases, and then we've said it's 0 at this vertical position. But generally it's got some angular momentum, so it will actually keep on turning and go past this vertical position. Now, if we don't have an alternating current, if the current keeps flowing in the same direction, at this point there's going to be a torque back in that direction, and so what we'll end up with is this coil kind of swinging backwards and forwards until it stops when it's vertical. But if we have an alternating current and it switches direction just as the coil gets past this vertical bit, it'll then feel a force in the opposite direction, so that will keep it turning until it gets to this point, at which point, if the current switches again, it can feel a force up there. So how to describe this? Let's say if the AC current has the same frequency, as the turns of the coil, turning of the coil, we can get the motor to turn continuously, which is in fact what they do when they're building motors. They get them so that they are turning in Australia at 50 Hertz, as that is the frequency that our current is supplied at. Problem 10. Now, in this problem, we're told that a power plant produces energy with a voltage of 10,000 volts. So let's just draw power plant. Here's the energy coming out at 10,000 volts. It's then transmitted over a long distance at a voltage of 250,000 volts. Okay, so it'll go here to a step up transformer. And then it goes long distance at 250,000 volts, and then it'll go down to a step down transformer where it comes out at 5,000 volts. And now part A of the question says, if the step up transformer has 200 turns in the primary coil, so we've got MP is equal to 200. This is going to be the VP, as this is the initial voltage. This is going to be the VS in this case, as this is the secondary voltage. And we're asked how many turns are there in the secondary coil. So we know that NP on NS is equal to VP on VS. What we're trying to find is NS. So this tells us that NS is equal to NP times VS on VP. So now all we need to do is substitute in. NP is 200, The secondary voltage is the 250,000. The primary voltage is equal to the 10,000. A lot of these thousands will cancel off, and then solving that we end up with 5,000 turns. Now in part B, we're asked if the secondary coil in the step-down transformer, so here NS is equal to 250 turns, how many are there in the primary coil? Now in this case, this is our primary voltage and this is our secondary voltage. So calculating, we need to get NP. We can see NP is going to be equal to NS VP on VS. The number of turns in the secondary coil is 250. The voltage in the primary coil is 250,000, and the voltage in the secondary coil is 5,000. Those thousands cancel out. 250 divided by 5 gives us 50, times 250 gives us 12,500 turns. Now part C. We're told that 0.5% of the power is lost in the long distance transmission lines. So 0.5 over 100, that's 0.5%, is equal to the power lost over the power transmitted. Now the power lost is due to the current and the resistance, so it's given by I squared R, and the power transmitted is equal to VI. So this I and that I will cancel each other out, and we need to work out what this current is. We're told that this resistance is 1,200, and we know that the voltage is 250,000. So rearranging this, we can see that I is equal to 0.5 over 100 times 250,000 over 1,200. And solving this on the calculator, we get 1.04 amps, or if we want it to two significant figures, 1.0 amps to 2 sig fig. And then we're asked how much power do they carry? Well, that's the power transmitted, this VI, so P is equal to VI, so that's equal to 250,000 times the 1.04. And solving that on the calculator, we get 260,000 watts. So that's how we solve that problem, and that's the end of this tutorial set.